Picture this. You're taking a molecule and placing it into a massive, unimaginably powerful magnetic field. We're talking, say, 1.41 Tesla. That is over 10,000 times stronger than a standard fridge magnet. You hit it with a blast of radio frequency energy, and you watch how its hydrogen nuclei, its protons, react. But here is the core mystery. Since every single proton is exactly the same fundamental particle, you'd think they would all resonate at the exact same frequency, right? Well, actually, they don't. They resonate at slightly different frequencies. Welcome to This Explainer, where we're going to unravel exactly why that happens and how we can use this quirky quantum phenomenon to decode the invisible 3D world of molecules. Here's our roadmap for today. We'll kick things off with a resonance frequency mystery, then move on to local diamagnetic shielding, the electronegativity effect, tackle the pi electron wildcard, explain magnetic anisotropy, and finally, bring it all together to solve the molecular puzzle.
Section 1. The Resonance Frequency Mystery. Let's look at the fundamental puzzle.
Okay, let's dive into this. If all protons are just standard hydrogen nuclei, why on earth do they resonate at different frequencies inside an NMR spectrometer? Well, the answer comes down to the fact that these protons don't exist in a vacuum. They are part of a molecule, which means they are completely surrounded by a cloud of electrons. And it's these electrons that put every single proton into a slightly different, totally unique electronic and magnetic environment.
So how do we actually quantify these different environments? We use a concept called chemical shift, which we represent with the Greek letter delta. Now, trying to measure exact, absolute frequencies is incredibly tough. We're talking about picking out differences of just a few hertz out of, 60 million hertz. So we don't even try. Instead, we measure how far a proton's resonance is shifted relative to a standard reference compound called TMS. We report this shift in parts per million, or ppm. This is brilliant because it gives us a field-independent measure, meaning that chemical shift value is going to stay exactly the same whether you're using an older 60 MHz machine or some massive, state-of-the-art 300 MHz research instrument.
Just look at how neat this is. Notice how different functional groups reliably show up at very specific, predictable chemical shift ranges on this chart. You've got aldehydes way down at 9 to 10 ppm, aromatic rings hanging around 7 to 8 ppm, and your simple aliphatic methyl groups clustering way up near 1 ppm. It's incredibly consistent. But to truly use NMR as a powerful structural tool, we can't just blindly memorize this chart. We really need to uncover the hidden rules behind why these protons sit exactly where they do.
Moving to Section 2, Local Diamagnetic Shielding, our local electron barriers.
I want you to think of the electron cloud around a nucleus as a literal shield. When you place a molecule into the giant applied magnetic field of the NMR spectrometer, the valence electrons around the proton are forced to start circulating. Just like an electrical current flowing through a wire, this local diamagnetic current generates its own secondary, induced magnetic field. But here is the real kicker. This induced field goes in the exact opposite direction of the giant applied magnet.
So, let's break down this chain reaction. The applied magnetic field causes those valence electrons to circulate. That circulation generates a countermagnetic field. Because of this counterfield, the proton is effectively shielded from feeling the full brute force of the applied NMR magnet. Experiencing a weaker net magnetic field means the shielded proton processes, or wobbles, at a lower frequency. And a lower frequency translates directly to a lower chemical shift on our chart, pushing it closer to 0 ppm. Simply put, the more electron density you have surrounding a proton, the stronger its shield and the lower its chemical shift.
Section 3. The electronegativity effect. Let's talk about shield-stealing atoms.
We've established that electrons are our shield. So what happens if a highly electronegative atom, like a halogen or an oxygen, attaches to the carbon right next to our proton? Step 1, it attaches. Step 2, because it's so electronegative, it acts like an electron thief, pulling the valence electron density toward itself and away from the proton. Step 3, with fewer electrons hanging around, the local diamagnetic shielding drops. And step 4, the proton is now stripped of its protection. It becomes deshielded, feels way more that giant applied magnet, processes faster, and therefore its chemical shift shoots up, moving further to the left on our chart.
And this brilliantly illustrates the direct relationship between electronegativity and chemical shift. Take a look at the top row for fluorine. As the absolute most electronegative element, when it attaches to a methyl group, it violently steals that electron density. This results in the lowest expected shielding, and therefore, the absolute highest chemical shift for those protons. Now, chlorine is slightly less electronegative, so the shift is high, sure, but not quite as high as fluorine. Bromine is even less, giving us a more moderate shift. It's a perfect, elegant trend. As electronegativity goes up, shielding goes down, and the chemical shift rises.
Part 4, the pi electron wildcard. Time for the rule breakers.
Okay, we have a bit of narrative tension here. If stealing electrons is the main way to get a high chemical shift, then notice the stark difference here. Your simple, everyday aliphatic protons attached to standard sp3 carbons sit quietly between 1 and 4 ppm. But look at aromatic benzene protons. They're just attached to standard carbon, yet they boast these massive shifts between 7 and 8 ppm. I mean, that rivals the shifts you see when protons are right next to highly electronegative atoms. But there are no highly electronegative atoms in benzene, so what on earth is stripping away their shield?
Well, the culprit is what we call the anomalous shift. Whenever protons find themselves near an unsaturated system, like the double bonds in alkenes, the triple bonds in alkynes, or the delocalized rings in aromatics, they exhibit completely bizarre shifts. And the one major thing all these unsaturated systems have in common, the presence of labile, easily moved pi electrons. Which brings us to Section 5, Magnetic Anisotropy Explained. We have to start thinking in 3D. When the pi electrons of an unsaturated group interact with the massive applied magnetic field, they circulate and create secondary fields that are anisotropic. Now, in electromagnetic terms, an anisotropic field is perfectly uniform. So an anisotropic field, that's non-uniform. Guide your eyes to the plus and minus zones on these diagrams. The plus zones are these conical areas where the secondary field directly opposes the main magnet. These are our shielding zones. But outside those cones, in the minus regions, the field lines loop back around and actually add to the applied magnetic field. These are the de-shielding zones. Ultimately, whether a proton is shielded or de-shielded entirely depends on where it physically sits, its real estate, in 3D space around that pi system.
Now, what's really interesting about this slide is how it brilliantly solves our benzene mystery. Notice the graphic on the left. The 6 pi electrons in benzene circulate to form a really powerful ring current. This current creates a massive shielding zone right through the center of the ring. But here's the thing, the protons aren't in the center. They are attached to the outside edges of the ring, and as you can see, those outside edges sit squarely in the de-shielding zone. The field lines are adding to the applied magnet, which is exactly why benzene protons are pushed all the way down to 7 or 8 ppm. On the right, you see a carbonyl group. Its anisotropic field has a totally different geometry, but the core rule remains. If a proton happens to be held in that negative, de-shielding space by the molecule's rigid structure, its chemical shift is going to spike.
Finally, Section 6, Solving the Molecular Puzzle. Let's decode these structures.
So, bringing this all together, the crucial takeaway is that we've established 3 golden rules to guide us. First, our baseline, high electron density, provides diamagnetic shielding, which gives you a lower precessional frequency and a lower ppm shift. Second, the electronegativity effect. Neighboring atoms that steal electrons tear down that shield, causing a higher ppm shift. And third, the wildcards. Pi systems generate complex anisotropic fields, where your specific 3D spatial position completely dictates whether you are shielded or wildly deshielded.
When you combine these 3 rules, you aren't just staring at random peaks on a graph anymore. Mapping these tiny parts per million frequency shifts is literally the master key. It allows us to infer exactly what atoms are nearby, how tightly electrons are being held, and precisely how the molecule bends and folds in space. It unlocks the entire 3-dimensional architecture of a totally unknown molecule purely by listening to the radio frequencies of its spinning hydrogen nuclei. It's like solving a giant invisible puzzle.
It really is a total marvel of quantum mechanics made visible. So the next time you look at an NMR spectrum, don't just see a bunch of squiggly lines on a page. Ask yourself, what invisible, overlapping magnetic fields are shaping this puzzle? Thank you for joining me on this explainer, and keep exploring the incredible molecular architecture all around us.